Hello, everyone, and welcome back. Today, we are going to be finishing up section 7.4, which encompass double angle, half angle, and product to sum identities. This is part 3 of our little digital series we've got going on. So, we're going to talk about product to sum identities today and some really just awesome applications of them. You guys know I'm a nerd. I love trig. I love math. I think it's so incredible, but like I really nerd out over not necessarily like diving into exactly how the applications work, but just like seeing and knowing that that's what math can do just like blows my mind. It's seriously so amazing, and I find out new things every day, and I'm like, how could somebody not love this? But yeah, so that's what we're going to talk about today. Is we've done double angle already. We've done half angle, so we're going to talk about product to sum identities with your host, me, Ms. Passmore. Aloha. It's nice and hot outside, so we're getting the vibes going. You know what I mean? So today, our learning objectives. Specifically, we're going to talk about the product to sum and sum to product identities, which are just the same thing except forward and backwards. So students will be able to derive and use the product to sum and sum to product identities. Now, I'm actually not going to show you how to derive them. It's in your textbook. I just want to keep it really short and sweet and like straight to the point so you guys can see the applications of them and how to use the identities themselves. But I have included where you can go if you would like to see the derivations of them. And also, we're going to talk about some really sick and radical applications while using identities. So at this time, I want to show you what you're going to be doing for your warm-up really quick. And then we'll segue back to this and finish with the presentation. So on your guys' HyperDoc, you'll see explore the following links and take screenshots of your screen. So there's 4 different links, and oops, I'm missing one. But there's 4 different links that you're going to go to. And today we're going to be talking about things that happen in waves. So here's a super cool GIF. Check that out. So this is light being processed through a triangular prism, a glass prism. So here's the light interacting, infracts the light right here, and then you can see the light waves and the color waves coming through. It's just super, super cool. Most excellent. But that's not one of the links I'm going to have you go to, actually. As a matter of fact, the first one is this one. So the sound of sine. So if you guys don't realize, sine function has a frequency that actually radiates a sound. So if you wanted to play sine waves, you can use a frequency as a base, and you can just kind of manipulate these things. So what I want you guys to do is you'll notice that this is a slider and it manipulates your graph. This is a slider and it manipulates your graph. This is a slider and it manipulates your graph. Try to look at these functions way back when we talked about sine, cosine, tangent. Notice what those values are. And then what I think is like the coolest thing is you can play the sound. So I'm just going to play, I don't know, I just slid these sliders somewhere, and I want you guys to listen to what it sounds like when I've manipulated the functions in this way. Isn't that crazy? So like that's kind of fun, and you can kind of play around and do all kinds of neat stuff. But I just want you to like play around with it and see some really cool applications and take a screenshot. The second one you're going to go to is the sound of sine waves again. So you get to pick a sine function, change the frequency, and mess around with that. Actually, I think you need to go to something else. Here's another one. Here's a preview of how you can see like the sine wave changing with the higher frequency and lower frequency. Here is the corresponding note to it in music, which I think is just absolutely awesome. And then lastly, the Fourier sound synthesis. Now, Fourier sequences are so crazy and so wild, and probably like one of the coolest things that I wish I studied more when I was in my undergrad. They're just like a powerhouse. You guys don't have to worry about it. It's a specific series that just can do so much. But so what you can do is you can change the amount of time. You can play with the frequencies. First of all, you can see how long it's going to play the noise. Play around with the frequencies, and it will eventually play a noise. And I just want you to move them around and take a picture of it and write something cool about it for those guys. So that's what you guys will be doing for your warm-up. Second part, you're going to be watching this video. So if you weren't sure what to do, you can refer back to here. Okie dokie. So let's get back into it. So today, again, we're going to be talking about product to sum and sum to product identities. And some of y'all are going to be like, well, why? I'm over this. Are we done for summer? Are we ready? Can we go? What's going on? So I just wanted to give you guys like a little background and some cool tidbits of information. Talking about these specific identities today happens so frequently in our natural world. So it's an ongoing phenomenon that like happens all of the time. Anything that travels in waves, usually if we're going to investigate, do a deeper dive, start to figure out the inner workings of why something works or why something does something in particular, why when you do one thing the other thing is a reaction of that, comes from some sort of product to sum or sum to product equation interaction. And I just think that is so crazy. So like, for example, things that travel in waves that we're very familiar with are like light waves, you know. um, Things you can see certain things because of how much light is being transmitted, right? Same thing with sound. So the sound waves of my voice right now that is being transmitted through my microphone, through my headphone, into my computer, into the software, out on your speaker, and however else you're listening is being transmitted by waves. And it's just crazy, like the process of actually how your body interprets my wave uses math. It's incredible. Like it's going to be an interaction of these sum to product identities or product to sum. Like it's so crazy to me that like math can take it that far. You know what I mean? It's so cool. I don't always necessarily want to know exactly how, but I like knowing that it can do that and it does model that, and like wow, that's so crazy, and like who'd have thunk it. Like that's why math is so beautiful. um Here's a specific example. Dialing a telephone, right? Y'all got phones. I know you do. I've seen it in my classroom, seen you guys, chatting, do whatever it is that you're doing on there. But when you pick up a telephone and you go to call somebody, no matter what kind of phone you're using, it could be, your cell phone, it could be a home phone, it could be your iPhone, it could be an old janky phone, it could be an Android. It literally doesn't matter. It could be like an old school Nokia that nobody has anymore that's like so vintage, like no matter what kind of phones you have, when you're picking up a phone and dialing on it, the sound you hear as you're dialing and calling someone on your phone is literally the sum of two sound waves interacting with each other. So I have my phone in front of me. I'm going to hold it up to my microphone here that's attached to my headphones, and hopefully you'll be able to hear just the noise. And as I press the button, just think about that is two sound waves crashing into each other, interacting in a product or sum, and the resulting sound that you hear as I press that button literally can be represented by these identities that we're going to be talking about today. So hopefully you were able to hear that. I didn't have any rhyme or reason. I just started pressing numbers on my phone, and those are the noises. So literally, as I pressed, my finger touched it, two sound waves crashed together, created that sound, and I can represent that sound by an equation. Super crazy, super cool. I'm like, mind blown. So awesome. I live for applications of math. I just think it is so radical. Also, why this is important is it's very useful in calculus. Oftentimes you get kind of pigeonholed and stuck in calculation equations because there's so many constraints when you're evaluating something that it becomes really, really difficult, or a function behaves really weird, to kind of move around in the standard way in which you would solve a problem. So, again, just like everything else that we've learned so far, it kind of just becomes a tool that we slip in our back pocket or have at our disposal to use when we are trying to manipulate equations, when we're substituting in different values. If we want to reduce or expand or evaluate functions, but I don't really have a bunch of information right now, I only have certain things. It's really something that we're going to use um, in as far as substitution, in which you guys have gotten really good at. So, and then some of you are still like, but why though? Right? Like, I just think this stuff is so cool, but like you don't. Hopefully, it's coming off that like I think this stuff is super not awesome, but some of you still might not be convinced. So just so you understand, like how crazy this is, it's like when I talk about light and um sound, things that travel in waves that we're comfortable with, it's a lot more complex than it seems. Like, it's not always just going to be a sine or cosine wave just chilling and moving through the universe, and that's how it's going to be representing these crazy phenomena. No, like, it's likely going to have crazy frequencies and totally different amplitudes, and based on this frequency and amplitude, something happens and a process occurs, and everything is just so much more complex. So as we zoom in on things and are learning about how the world works and think why things are true and why did this happen and how come, and there's just all of these absolute truths at the bottom of things. We've been trying to describe our world from the beginning of time, practically. But when you dive really deep, you can actually find that like math is at the heart of it. So, sound wave and light waves, right? Here is a pictorial of a really, really fuzzy, I apologize, picture of light waves. Okay, so down here you'll see here's our scale. Here's short wavelengths. They have a higher frequency. Here's longer wavelengths with a smaller frequency. They're taking a lot longer to complete their cycle. And then down here you'll see that these are all of the like the measurements of them. So way down here, high frequency, this is light, but in terms of sound, sometimes as you get older, your ears don't work as well, and you can't hear high frequency noises, but your dogs can, or your cats can, or whatever, because they have a heightened sense of sound. They have that sense is much stronger than ours, right? Down here, a really high frequency light wave is a gamma ray, which is something I'm not going to get into it, but it's really cool, super nerdy. Then X-rays are there. So when like the process of seeing your bones, if you got crazy and broke a bone, your X-rays are way down here at like these 10 to the negative 3 hertz is what I think that says. Ultraviolet rays, UV rays, turning on a UV light, having like, a little glow stick party or whatever. UV, the way that we're able to actually see that is way down here. And then this teeny tiny bit from this minimum to this maximum value represents right here, right on this part of the wave, represents visible light and colors that we're able to see. And like, that's so crazy. And then you have infrared light when you're living in college and you're microwaving all of your food, microwaves as you're driving down the road, listening to the radio. Your radio waves are a lot longer. It's just like, it's not always going to be so nice, but like as you dig deeper, it's so much more complex. Um, but basically, these identities that we're going to see in a few minutes is literally just breaking down the waves and seeing how these waves are transmitted. So, how visible light is transmitted, how a sound is transmitted, comes down in one way or another, or some manipulation deals with these product to sum or sum to product identities. And it's seriously so fascinating to me. Um, so here's light entering a glass prism and then producing the colors of the rainbow on the color spectrum, right? And outputting visible light. If you've probably seen something like this on Pink Floyd, that's one of their album covers, which is super cool. But now you like know that there's like math behind it, like the way that this light interacts with the glass and then the light refracts and changes has a mathematical process that can be represented by these waves, this part of the wave right here. And if we're starting at the bottom and going up, negative cosine, right? Crazy. Here's another like still image of some light waves, which I just thought was really cool and pretty. And people in photography use still images to get this all the time. It has to like their camera has to shutter really quickly in order to capture these, which is I think is super cool. And like your phone is actually capturing light waves. And then sometimes they turn out to be in the form of a wave as well, which I just think is so awesome. Um, yeah, so I'm going to spare you the details on how these product to sum identities are derived. They're on page 685 if you care or you're interested. But I'm really just going to show you like how they can be used, and they're not going to be always as exciting and wonderful as all of these different things I'm explaining here, because the fact of the matter is those are super complex. And we're just chilling on pre-calc, but we want to see how they're used. So let's get to it, shall we? What you're going to need. Okay, you're going to need some notes here. You're definitely going to want to write down the product to sum identities because, dude, they are like exactly the same. They look so similar. It is absolute insanity trying to keep things straight. So get out a piece of paper and a pencil. You're going to need it. You should be taking notes anyway, hopefully. But the product, excuse me, product to sum identities are as follows. Now, I'm not proving you how they're being derived, so you get to take this as is. You're welcome. Take it as is. How things appear is how they are. So if I have a cosine alpha times a cosine of beta, I'm going to have cosine of alpha minus beta plus cosine of alpha plus beta with 1/2 on the outside. So that's one of them. This is going from a product to an expanded sum. Simplified, expanded, right? Now I could also have sine times sine. Sine alpha times sine beta, a sine times a sine, two different angles. It's going to be 1/2 times the quantity of cosine alpha minus beta minus cosine. So sine times sine deals with two cosines and a subtraction sign. Cosine times cosine also deals with cosine with addition sign on the inside. You could also have either sine times cosine or cosine times sine. So sine times cosine is going to be 1/2 times the quantity of sine of the sum of those angles plus the sine of the difference of those angles. And lastly, you could do cosine times sine is going to be 1/2 of sine times the sum of those angles minus sine times the difference of those angles. So now, just because I'm a little crazy and I like to start to recognize patterns, I'm going to underline all of the things that have cosine and sine, just so it can become a little bit more apparent. It just helps me in recognizing different things. So make note that cosine times cosine or sine times sine, they both have cosine both times, just plus and minus. Every single function has 1/2 on the outside. When you do sine times cosine or cosine times sine, doesn't matter if the combination of the two, they both deal with sine. So that's just kind of like some tidbits on how you can get comfortable with remembering what the product to sum identities are, should you not have your piece of paper in front of you as you're working through them. I'm a big proponent of like just giving you the resources and then you working through it. But maybe you don't have one in front of you, or maybe you're not taking notes like you should be. And so that's a way to make sure that you can kind of start to memorize these identities or identify which one's which. So write this down, take a little note to remind you in case you didn't know. Write this down. That's Strode Straight, ladies and gentlemen. Woo! If you don't know that song, Listen to it. It's literally called Write This Down. Every time I ask someone to write something down, I think about that song, and it makes me giggle a little bit. I can't play it for copyright purposes, but go check it out. Maybe I'll leave the link somewhere or something. Um, so let's use these. Let's put it to work. Okay. Here's example 1. Rewriting a product as an equivalent sum using an identity. So our objective here is to write the product 2 times cosine of 27t times cosine of 15t as the sum of 2 cosine functions. So not only does it tell us straight up that we have to use, we want to write it as a cosine plus a cosine, right? And if I'm looking at my formulas, the only area where they had cosine, 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 and a sum, it's not this one. This one has sine, and this one has sine. It's going to be here. But also, maybe say it didn't tell you how it was to rewrite it as a sum, perhaps. Notice that you have cosine times cosine, and out of all of these, cosine times cosine is really your only option. So you would have to use this identity. So to get us started on this is we're going to use a direct application of the product-to-sum identity. And now notice that this comes first, like cosine times cosine, cosine of alpha times cosine of beta. Alpha is clearly going to be 27t, and beta is going to be 15t, just because this is the first number that pops up, an angle. This is the second number, an angle that pops up as well. So just rewriting cosine alpha times cosine of beta is equal to 1/2 times the quantity of cosine of alpha minus beta plus cosine of alpha plus beta. Just rewrote that guy, threw some color on it. Now let's substitute in the fact that we don't have just cosine alpha times cosine beta, but I actually have 2 times cosine alpha and cosine beta, right? I have this number right over here. So if I just multiply by 2 in this identity, here's my 2, and here's my 2. This is what I've got going, and this is what I want to figure out. Plugging in alpha is 27t, beta is 15t. We're going to start evaluating the right-hand side. Now, 2 times 1/2, that's going to cancel each other out, right? 2 times 1/2, boom, boom, that cancels out. 27 minus 15 results in 12. 27 plus 15 results in 42. They all have variable of t attached to it. So finally, the product 2 times cosine of 27t times cosine of 15t is equal to cosine of 12t plus cosine of 42t. I rewrote it as a sum. Here's the addition sign right here. The sum tells me I hit my goal, little check mark, maybe, a happy face or something like that. And we did our goal. It's not too bad. Like I said, I think you guys are not going to hate this section as much as some of you have been hating it, just because it's very applied and you guys like plugging stuff in and we're comfortable with evaluating. Now, I got some bad news for y'all. Sometimes, and you've seen this, we have to work backwards. We have to work in the other direction, just for different problem solving issues that we might encounter. So sometimes we do need to work backwards. Sometimes we got to work in the other direction. So instead of having a product and going to a sum, sometimes I have a sum and I need to go to a product. So again, I'm not going to show you how to derive this because I just want to get to the nuts and bolts of how to use it. But it's on page 685 if you care to check it out. Essentially, you just use the product-to-sum equation and change the variables around, do some algebra, and you end up with the reverse. So, piece of paper, pencils, sum to product identities again. Gonna need to write this down. And something to note again is they're very, very similar. Super, super, super close. So, making note of those things is important. All right, if I have cosine of an angle plus cosine of another angle, or cosine of a radian plus cosine of another radian, right? If I have cosine plus cosine, it is equal to 2. times cosine of u plus v over 2 times cosine of u minus v over 2. Remember, this is multiplying, multiplying, multiplying. Similarly, if I'm going to add sines, I'm going to say sine plus sine, sine of one thing plus sine of another, sine of u plus sine of v is equal to 2 times sine of u plus v over 2 times cosine of u minus v over 2. The third identity is sine of u, oops, I wanted a different color. Sine of u minus sine of u, or sine of v. So sine of one angle minus the sine of another angle is 2 times cosine of u plus v times sine of u minus v. So cosine comes first in this instance. And lastly, if you have a cosine of an angle minus another cosine of an angle, you actually end up with 2 times, remember these is all multiplication, sine of u plus v over 2 times sine of u minus v over 2. Now, something you might have noticed is that the first term is always u plus v over 2. U plus v over 2. U plus v over 2. These are some patterns that you can start to recognize to help yourself as you're working through these. And then the second one is u minus v over 2. U minus v over 2, u minus v over 2, and u minus v over 2. So I start to kind of see identities in patterns. They all have 2's in front of them as well. So 2 times all of this stuff, it's not really going to go away. We've got a 2, 2, 2. The only difference is cosine. Subtracting off cosine ends up in a -2. That one's kind of different. But I start to piece them together and start to recognize patterns. So again, you're going to want to write this down. Or write that down, Patrick, write that down. So make sure if you don't have these written out, you don't have to color code them like me. I just find it helps my brain. Have these at your disposal because again, we gonna do an example. Okay? All right. Pause now if you need more time. Okay. So example 2, rewriting a sum. So going from a sum to a product as a product using identities. So notice I have the sum to product up here still in case you didn't quite finish writing them out. This is kind of a little bit of a different situation. Okay, this is all one slide, my bad. So if you're given y1 equals sine of 12 pi t and y2 is sine of 10 pi t, express the sum y1 plus y2 as a product of trig functions. So this is our goal. Write it as a product, and now notice that I've got y1 times y2 sine plus sine. The only time where I'm adding 2 sines together is going to be with this equation. So we're just going to use a direct application of the sum to product identity. So the first thing that comes up is this value. So that's going to be my u. U is going to be 12 pi t. And the second thing that comes up is 10 pi t. That's going to be my v, my second thing that comes up. So if I just rewrite the equation entirely, we have sine of u plus sine of v is equal to 2 times sine of u plus v over 2, cosine of u minus v over 2. Again, I just rewrote that identity that's literally taken from up here and just color-coded just to help us identify some substitutions. If I plug in u and v, I get the left-hand side as sine of 12 pi t plus sine of 10 pi t is equal to 2 times sine of 12 pi t plus 10 pi t over 2, cosine of 12 pi t minus 10 pi t over 2, and you can see how we just literally substituted in u and v. Doing a little bit of algebra, 12 plus 10 is 22 pi t over 2. 12 pi t minus 10 pi t is 2 pi t over 2, so I'm left with 2 times cosine of 22 pi t over 2, cosine of 2 pi t over 2. And as I do some math, 22 divided by 12 is 11. 2 divided by 2 is just 1. So my final result is then 2 times cosine of 11 pi t. Cosine pi t. And this should have been sine. Oops. Typo. My bad. Gosh, this slide got all jacked up. This should be sine. 2 times sine of 11 pi t. My bad. So crazy. I thought I fixed the typos on this. My bad. I'm so sorry. 2 times sine 11 pi t cosine pi t. So, some applications. Projectile motion obviously has a lot going on if you think about something being thrown, an object being thrown, shot, kicked, dropped, or whatever, given some sort of initial velocity, but it's lacking a continual source of propulsion, so it's not like a jetpack or something like that, or it's not a plane. Although it's in motion, it's not necessarily a projectile. If you think about the fact when we throw things, it's like a parabola is often how we're using it, but we can also think of that as part of a sinusoidal wave as well. So, like I said, here's something in projectile motion. Here's this guy kicking a football, right? And it starts off here. His initial velocity is the kick from his foot, the torque from his foot, going off at a certain angle, theta, and then it shoots up. It doesn't have anything propelling it forward, so it comes to a peak and then falls, right? This is how I typically introduce parabolas and things like that, but it's also like the top half of a sine wave. So we could use that. Here is like a real physics type image with the velocities, our angle. We're evaluating different things, but just to show you how this image of something very common can become this little piece of mathematical information. And then we could further use it with these identities that we've learned in this section. So here's something about projectile motion. If air resistance is ignored, which oftentimes it is initially ignored when trying to figure something out just for simplification processes. If you guys go into physics, you'll see that happens a lot. We'll overly simplify. The range of the projectile, so how high the projectile is going to go. Again, this would be the range, like from here to here, right? Range is y values. The range of the projectile depends only on its initial velocity over here and the angle at which it's propelled. So if that's all we need to figure out how high an object is going to go, where it's going to peak at, we can use this function. R theta is equal to 1 over 16 v squared sine theta cosine theta. So write this down as well. You're going to want to have this written down. This little piece of information. We're going to use it in the next example, actually, and kind of mess around with it and find out some applications of using this. Notice that this is sine times cosine. That's a product. So here's our first example. Using identities to solve an application show. So use an identity to show r of theta equals 16v squared cosine, or sine theta cosine theta is equivalent to r theta is equal to 1 over 32 v squared sine of 2 theta. So I want to use some of the identities that we've talked about in this section so far. Remember, we have half angle, double angle, and product to sum so far to show that this is equivalent. And it's almost the same, except the denominator changes from 1 over 16 to 1 over 32. And then this piece of information over here changes from sine cosine to just sine of 2 theta. So we're going to have to use a couple different pieces of information. The solution is noting that it changed to a double angle identity over here. So we're probably going to have to use a double angle identity. And we're going to use this coefficient also is part of a double angle, like 1 over 16 is very similar to 1 over 32, right? If I took half of 1 over 16, that's 1/32, right? So 1 over 16 is a double angle of 1 over 32. So first thing I want you to know is that 1 over 16 is equal to 2 times 1 over 32, right? 2 times 1 divided by 32 reduces to 1 over 16. So I'm going to use this fact. This is something that's true. It is an equivalent form. I'm going to plug that guy right in. But the equation for projectile motion is 1 over 16 v squared sine theta cosine theta. So I don't quite have this. I want to show this is equal to 1 over 32 v squared sine 2 theta. So what I'm actually going to do is just change, since I know that 1 over 16 is equal to 2 times 1 over 32, I'm literally going to substitute in 1 over 16 and 2 times 1 over 32. So that's just a direct substitution. V squared sine theta cosine theta. And I'm manipulating the right-hand side to hopefully get to this, right? 1 over 32 v squared sine 2 theta. So now that we're here, I can rewrite this. This is 2 times 1 over 32 times v squared times sine times cosine. I can move around. The associative property of multiplication is that it doesn't matter the order. 1 times 2 times 3 is 6. And it doesn't matter if I did 2 times 3 times 1, 2 times 1 times 3, 1 times 2 times 3, 3 times 2 times 1. It doesn't matter. It's always going to be equal to 6. So I can rewrite this in a sneaky way. I have 1 over 32. I have multiplied by v squared, which I had before right here. I moved the 2 to the third position, sine theta cosine theta. So the reason I did this is because now I have a double angle identity. 2 sine theta cosine theta, that you'll have to go back to when we were talking about double angle identities and substitute that in. So that's what we're actually going to do. I am going to emphasize that I'm grouping these these three things together, 1 over 32 v squared 2 sine theta cosine theta, because I'm going to use the double angle identity to substitute in for this form. Looking back at double angle identities, that is just going to be this right here is equal to sine of 2 theta, sine of 2 theta. So if I plug that in, that's a really bad theta. I have 1 over 32 v squared sine 2 theta, which is exactly what I wanted to do. I wanted to show that it was equal to that, and I was able to get that result by doing a little bit of like straight up equivalency, a little, and also noting like, hey, that's actually kind of like a double angle idea that we use, then actually using a double angle identity and manipulating myself back to where I want to go. So something important about this example is think about what we're working with. Multiplication is associative, meaning it can move around. Use that to your advantage should you need to. Sometimes you might not need to, they might just fall into place. But sometimes if you get stuck, think about, are they being added together, subtracted, multiplying, dividing? How can I manipulate these around to get maybe something else that I can plug in a different form for? Example 3b, using identities to solve an application. So using the formulas in part A, if a projectile is thrown with an initial velocity of 96 feet per second, how far will it travel if theta is 15 degrees? So we're going to use the velocity formula. This is what was given to us, 1 over 16 v squared sine theta cosine theta. And we just figured out that this is true. This is equivalent to this, so either of these forms will do. This one's a little bit more simple, so we're going to work with this guy. And then we're going to literally just use this fact that it's V is 96, theta is 15, and plug it right on in. So here is my equation. Plugging in 15 degrees and 96 feet per second. I get r of 15 is 1 over 32, 96 squared, sine of 2 times 15. 2 times 15, of course, can be simplified to 30, so I have 1 over 32 times 96 squared, sine of 30 degrees. Oops. Sine of 30 degrees. Then 1 over 32, 96 squared is 9,216, and sine of 30 degrees evaluated is 1/2, so I'm plugging that in, ends up giving me 1 over 64 times 9,216, and if I take 9,216 divided by 64, I end up with 144 feet. Therefore, I just used this crazy velocity formula, which was a sum or a product of sine and cosine and some actual values to figure out if a projectile is thrown at a 15-degree angle and thrown at the velocity of 96 feet per second, it's going to travel overall 144 feet. So if I am, let's just say I am throwing a baseball at a 15-degree angle, which I think would be really hard, but I have a lot of force to it. 96 feet per second is my velocity. That baseball is going to go 144 feet. Now, that's not realistic for me. First of all, it would have to shoot out from something else. I don't even think that's humanly possible. But just to give you like kind of context to what that kind of problem might look like. Maybe it's propelling out of when you go to the batting cages. Perhaps that's how far the ball goes. If they're, 144 feet, it's kind of far. If it's being propelled at a 15-degree angle at 96 feet per second, it's going to go 144 feet away from that device that's shooting out the baseball. Neat. Part C. From the results of Part A, determine what angle theta will give the maximum range. So using Part A, which was just using an identity, and then the fact that we have using that identity, how high is this baseball? Let's just call it a baseball projectile. How high is this baseball going to go into the air? So the first thing that we need to know is that for any velocity, v, r theta is going to be maximized when sine of 2 theta is a maximum. Now, that's just going back to the identity saying that we initially had 1 over 16 v squared sine theta cosine theta, and we found out from parts A that that's equal to 1 over 32 v squared sine of 2 theta. So since I have that equation, I must maximize it at that second half of the equation, which is where I get 2 theta. Now, thinking about this, when sine of 2 theta is going to be maximized, this is going to happen when it's equal to 1, right? Because thinking about sine, the highest value that sine can be on the unit circle is 1. Where does that happen? That's going to be at 90-degree angle. Sine of 90 degrees is 1. So if I have sine of 2 theta has to equal 90 degrees, or we're dealing with a 45 degree angle. So the maximum range is achieved when coming out of that baseball thing, if it's being released at a 45-degree angle instead of 15, it is going to be the highest value that the projectile is going to go. So remember, it kind of takes a trajectory pathway. This value here is dependent upon this angle measure here. So let me just verify it and show you. Like, let's say it's still the same situation. It's the baseball example. Coming out at the baseball cage is that little machine, right? Still coming out at a velocity of 96 feet per second, and 45 degrees is when it's going to be maximized. So if I plug this into my equation, 1 over 32 v squared sine 2 theta, substitute in v is 96 feet per second, theta is 45 degrees. I plug this in. I end up with 1 over 32 times 96 squared, sine of 90 degrees. We know this is going to happen. Sine of 90 degrees is 1. So 9,216 divided by 32 reduces to 288 feet. So the height, right, the range, the height of this projectile is 288 feet. That's the highest point that it's going to reach. That's the highest point that coming out of a barrel at 96 feet per second squared, if it's 45 degrees, it's going to go 288 feet in the air, which is crazy, wild. You don't really need that unless you're like a superstar. But super cool. And here's a picture of a graphing calculator that shows this is the graph. This is 45-degree angle right here. So this is my 45-degree angle. Remember, I was asking for the range, the highest point. If it's being propelled at 92 or 96 feet per second squared, this is the path of the baseball. Its maximum height is right here. And this height, based on the scale, is 288 feet. So that's what we're talking about, 288 feet. One more application and a quick one of it is sound waves. Again, this is something that happens in everyday life. It's super complex, but cool. So a lot of the links that I sent you for your warm-up are sound waves of just how things are interacting with one another, right? Here's a clip of like a sound wave that you might see on a voice recording. Here is something from a speaker going into your ear, and notice that the sound is like propelling from the speaker in dispensed particles right here. It's just they're pretty close together. Then a space in between each beat, another sound, and that everywhere that these peaks are, that these pieces of dense particles or sounds hitting the air actually results in this sinusoidal peak, and this is something coming out at a constant rate. So this might be like a steady beat, like boom, 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 or something. I don't know. Something like that. And as you start to see like a 3D model imprinted on top of a sound wave, so in the background here is a sound wave, you can start to see how there's a lot of different sinusoidal waves that are interrelated into sound. So, example 4. We are going to use the sum to product identities to solve an application. So, like I said, remember when we were talking about the phone, okay? Here, down at the bottom left, is the dial pads on your phone and the corresponding cycles per second that the sound wave frequency has. So, on a touch tone phone, the sound created by pressing the number 5. So I'm going to do that right now. That sound is produced by combining a sound wave with frequency of 1336 cycles per second with another wave having 770 cycles per second. So another wave with the frequency of 770. So notice where the number 5 is on this pin pad right here, right? So everything in this row has 770 cycles per second. So 4, 5, and 6, they all have a frequency of 770 cycles per second. But additionally, everything in the second column right here has 1,336 cycles per second. And number 5 happens to fall right smack dab in the middle. So since it's overlapping these two, when you press the number 5 right here, that sound is produced by combining a 1336 cycle per second frequency wave with a 770 cycle per second frequency wave. So the equations would be cosine of 2 pi of 1336t and cosine of 2 pi 770t for each wavelength, right? So because I am in because I am in row 2, pressing 5 can be represented by cosine of 2 pi of 1336t. Notice I just take that little number. And similarly, since I'm pressing 5 and it resides in row 2, it's going to be cosine of 2 pi times 770t. So if I added those two together, because that's how that sound is happening, is it's those two sound waves crashing into each other by addition, I get y1 plus y2 is cosine of 2,672 pi t plus cosine of 1540 pi t. So I got those numbers from 2 times 1336 is 2,672. And additionally, 2 times 770 is 1540. So just so I don't lose you there. That's where that comes from. So the goal is to rewrite this sum as a product. So I've got a cosine plus a cosine. I need to rewrite this sum as a product. So I need cosine plus a cosine. Looky here. First one will do it for me. So let's just use that application. Let's directly apply it. Rewriting u is going to have to be 2,672 pi t. V is going to have to be 1540 pi t, just because that's the order they come in. And if I write out that equation, right, I take this all the way down here, we get cosine of u plus cosine of v is 2 times cosine of u plus v over 2 times cosine of u minus v over 2. And now let's just plug in what u and v are equal to. So the right-hand side is going to become 2 times cosine of u plus v over 2. So 2 times cosine of u plus v over 2 times cosine of u minus v over 2. U minus v over 2. Now let's do some algebra. 2,672 plus 1540 reduces to 4,212. 2,672 minus 1540 results in 1,132. They both have the units of pi t, so make sure you keep that. The result is 2 times cosine of 4,212 pi t over 2 times cosine 1,132 pi over t divided by 2. I notice these are both even, so if I simplify these by dividing the numbers by 2, I end up with 2 times cosine of 2,106 pi t times cosine of 566 pi t. Yay! So I rewrote the sum as a product, right? This is 2 times cosine times another cosine. That is all a product, and that's what I set out to do. All right. I will see you guys later. And I hope you thought this section was interesting. I know I sure do. And I hope you don't have any trouble with the homework. But if you do, remember, reach out to me. I try my best to get back to you as soon as possible. And hope you guys have a great day. Bye.